Good morning all of you. My name is Ashutosh and I am working as an assistant professor at Babu Banarsidass University, Lucknow. In this particular lecture, we will discuss about various generation and detection methods of amplitude shift keying, frequency shift keying, and the phase shift keying. These are the outlines of today's lecture. We'll start up with the introduction, in which we will discuss about the basics of modulation, and we'll also discuss about why do we actually need digital modulation techniques. Then we will discuss about various types of digital modulation techniques, in which we will discuss coherent digital modulation techniques and non-coherent digital techniques. We specifically mentioned that in digital coherent modulation techniques, we actually required the carrier information at receiving side too, whereas it is not the compulsion while we are having non-coherent digital modulation techniques. In coherent digital modulation techniques, we will discuss various types of generation methods of ASK, PSK and FSK, and in non-coherent digital modulation techniques, we will discuss about ASK and FSK. We will also mention why we do not have non-coherent digital modulation techniques for PSK. Then we will focus over applications of ASK, FSK and PSK in human life. Then at last, various advantages associated with the digital modulation techniques. So till now we have studied about various types of analog modulation techniques, in which we have discussed amplitude modulation, frequency modulation and phase modulation. We have also studied various pulse modulation techniques. In analog pulse modulation techniques, we have studied PAM system, PPM system and PWM system. Whereas in your digital pulse modulation techniques, we have studied pulse code modulation system, adaptive delta modulation, differential pulse code modulation and other things too. So we'll start up with the modulation. Modulation is the process by which some of the characteristics of my carrier wave, such as its amplitude, phase or frequency, is being varied as per the amplitude of my message signal. We always take the amplitude of my message signal because we are only concerned with the information, and information is directly proportional to the amplitude of my message signal. If I have to transmit a digital signal over a longer distance, then we need continuous wave modulation techniques. Since we have to match the channel conditions, that is why we needed continuous wave modulation technique. Our available channel is analog in nature and it only supports analog signal to transmit through it. In digital communication, the modulation process involves switching or keying the amplitude, frequency or phase of the carrier in accordance with the input data. If you are talking about binary sequences or binary data, we are only having two levels, either high or low, to represent 1 or 0. That is why we are saying that on that basis there exists three basic modulation techniques: amplitude shift keying, frequency shift keying or phase shift keying, because depending upon the input signaling stream, the data actually switches. Either that switch or keying exists in the amplitude or frequency or the phase. Suppose we are transmitting one amount of amplitude for the binary sequences 1 and another amplitude for the binary sequences 0. Similarly, we are passing a different frequency for representing 0 and different frequency for representation of 1. Similarly, there exists a phase change in the carrier waveform when we are passing 0 or 1. So before we start up with various generation detection methods of ASK, PSK and FSK, we must have to discuss what are the desirable characteristics of digital modulation technique. So the desirable digital modulation technique should provide low bit error rate at low SNR. Means if the received signal strength is not quite high or the SNR is quite low, then also it shouldn't gone through, it should possess lower bit error rate. Means majority of the bits sequences should not gone through the error. It should perform well in multipath fading environment. It occupies minimum amount of bandwidth so that we can maximize the capacity. It should be easy and cost effective in the implementation. Since all those points that we have mentioned above, they cannot be achieved simultaneously. So depending upon the requirement, we have to take a trade-off. Digital modulation techniques could be of two types. Number one is your coherent digital modulation techniques, and another one is your non-coherent digital modulation techniques. As we had already mentioned that in coherent digital modulation technique, we actually need the carrier at the transmitting side and the carrier at the receiving side should be in complete synchronization. In coherent detection, the locally generated carrier at the receiver is phase locked with the carrier at the transmitter, and the detection is actually done by correlating between the received noisy signal and the locally generated carrier. The coherent detection is also called as a synchronous detection, since we are talking about the synchronization between the transmitted carrier and the received carrier. Whereas in non-coherent digital modulation techniques, we do not need the carrier at the transmitting side and the receiving side. They are in complete phase locked. The advantage of such type of system is that the system becomes simple, but the drawback of such system is that error probabilities increases. Binary amplitude shift keying. The most basic form of ASK involves the process of switching the carrier either on or off in correspondence to the sequence of digital pulses that constitutes the information. Information is of binary sequences. For the representation of binary sequences, we are either providing high level or lower level. So one binary digit is represented by the presence of carrier and another binary digit is represented by the absence of carrier, whereas the frequency remains fixed. Means if we have to pass on logical sequence or bit sequences 1, then we are actually passing the carrier, and if we have to transmit 0, in that particular case we will not pass the carrier. So there is a switching or keying between the amplitudes. Means for representing 1 we are having the carrier which is having some amplitude, whereas for the transmission of logical sequence 0 we do not pass any carrier signal. It means at that particular position the amplitude will be 0. So we are having a switching sequences of carrier amplitude and no carrier. That is why we are also call it as a on-off keying. So this particular figure shows the amplitude shift keying waveform. This particular sequence 1 0 1 1 0, let us say these are the binary stream which we have to pass it on, and for line coding techniques we are representing it higher value of the pulse as 1 and lower value of pulse as 0, and this particular wave corresponds to the carrier waveform, and we actually producing the switching in this particular carrier. It means for 1 we are having carrier, for 0 we do not have carrier, for again 1 1 we are having the carrier, and for 0 we do not have the carrier. This is the mathematical representation of your ASK. ST is the output waveform, which is the multiplication of message signal MT, which is nothing but your 10110 with cos omega CT, which is your carrier waveform. So if the value of MT is equal to 1, then we'll having the carrier which is equivalent to A cos omega CT, and where the message signal is 0, we'll be having the product output of 0. So M of NTB turns out to be A of 1. I mean, for representation of 1 we are having 1, for representation of 0 we are having 0. This particular slide shows how we're going to generate ASK signal. So for generation of ASK signal we will be using a product modulator which is having the input side at the binary waveform input, and another input of your product modulator is the carrier waveform which is generated by the oscillator, and the output will be having ASK waveform ST, which has been mentioned in the last slide. So this is how we actually generate ASK signal. ASK signal may be generated by simply applying the incoming binary data represented in the unipolar form and the sinusoidal carrier to the two inputs of the product modulator. The resulting output will be the ASK waveform. Then this slide shows how we'll coherently demodulate the ASK signal. Initially we'll be having a product modulator, and the one input of the product modulator will be a binary ASK waveform, and the second input will be a carrier waveform. Then the output is passed through the integrator, which integrates the product modulator output in the duration of TB, where TB represents the bit duration, and again this particular signal is passed on through a decision device, which depending upon the threshold value decides whether transmitted bit was 0 or 1. So this is the coherent method of ASK detection. This slide shows actually the explanation of how we are receiving ASK signal. The demodulation of binary ASK waveform can be achieved by coherent detector. It consists of a product modulator, which is followed by an integrator and a decision-making device. The incoming ASK signal is applied to one input of the product modulator, and the other input of the product modulator is supplied with a sinusoidal carrier. Then the output is fed to the integrator, and the integrator integrates the output of the multiplier for the successive bit intervals TB, as we have mentioned earlier, and essentially performs a low-pass filtering. So the decision-making device compares the output of the integrator with the preset threshold. Then it will compare it. Depending upon if value is high, then it makes the decision in favor of 1. If it is low, or the integrator output is below the threshold value, then it produces the output as 0. The coherent detection makes the use of linear operation. In this method, we have assumed that the local carrier is in perfect synchronization with the carrier used at the transmitter. Although this is not always be the case, we'll be having some sort of delays or phase differences, but in this particular case we are assuming that they are in complete synchronization. Disadvantages of ASK signal. Although generation of ASK is easier in comparison to FSK and PSK, and the bandwidth requirement is also equal to twice of RB, but it has high probability of error, as mostly error added on over the amplitude. I mean, noisy signal are actually added up with the amplitude, so it may affect the signal strength or amplitude of the signal, and in this particular case we are passing our information through the amplitude switching. So there may be the cases that noises will be added on over the amplitude, such that for transmission of 0 we can detect as signal 1, and for 1 we can detect it as 0. Means probability of error might be high. If probability of error is high, then noise immunity is obviously lower side. SNR is less. The most basic form of PSK involves the process of switching the carrier either in phase or out of phase in correspondence to the sequence of digital pulses that constitutes the information signal. It means here we'll be having switching of carrier pulse either in phase or out of phase, depending upon what type of binary information we have, either 1 or 0. One binary digit is represented by the carrier wave, and the other binary digit is represented by 180 degree out of phase of the original carrier, whereas the frequency remains fixed. So again we'll be using the similar type of carrier, but the only difference is depending upon the binary stream 1 or 0, its phase get changed. This particular slide shows the pictorial view of BPSK signal, how we'll actually going to represent this BPSK signal. So again we'll be having information bits 1 0 1 1 0, but one thing has to be mentioned here, that in this particular scheme we'll be having bipolar scheme in comparison to unipolar scheme as we have in our ASK signal. It means for representation of 1 we'll be having positive voltage of pulse, whereas to represent binary digit 0 we will not having the 0 DC value, we'll be having some negative DC value. Then again higher value of pulse for 1, higher value of pulse for 1, and negative value of pulse for 0. This is the carrier waveform which we are exploiting for transmitting our data. Again we can see that in this particular figure, that's for transmitting 1 we'll be using this type of carrier. Then as the transition when bits from goes from 1 to 0, then we'll be having 180 degree out of phase. The carrier starts from here. It will not continuously grow like this. It is just started from here, which shows 180 degree out of phase. Again, whenever transition exists, this particular wave does not continue like this. Again, it produces 180 degree out of phase from the original signal. So 1 to 1 means no change, carrier will get continue. Again 1 to 0, 180 degree phase difference. So this particular equation shows the output waveform of my PSK signal. Again, ST is equal to MT into cos omega CT, where MT is the message signal and cos omega CT is the carrier waveform. So whenever the value of MT becomes 1, means if we have want to transmit 1, then the output wave equation will be A cos omega CT, and when we have to transmit 0, then the output wave equation turns out to be A cos omega CT plus pi. It means 180 degree out of phase in comparison to the original carrier waveform. So now this particular slide gives the idea about how we'll actually going to generate the PSK signal. So for generating PSK signal, we'll be having binary input signal, means bit stream of 0 and 1. Then we'll be passing this particular signal into unipolar to bipolar converter, which can convert my signal into bipolar format. Then this bipolar formatted signal goes to the product modulator. The second input to the product modulator will be a carrier waveform, which is generated by an oscillator, and the output waveform will be the ST waveform, as we have discussed in the earlier slide. So this overall gives the insight how you're going to generate PSK signal. So for generating PSK signal, we first convert the unipolar binary signal to the bipolar signal stream. Then the generated bipolar signal data and the sinusoidal carrier are applied at the two inputs of the product modulator. The resulting output of the product modulator will be the PSK waveform. So now this figure shows how you're going to detect PSK signal. Although at very first look this figures looks quite complex, but this is quite simple. We usually study the detection of BPSK waveform in two parts. Number one is your carrier recovery and another one is your synchronous detection. So the upper block, this particular upper block, which is shown by a purple color rectangle, is responsible for generating the carrier waveform or carrier recovery, and this green color rectangular box is responsible for synchronous detection. Then initially we'll apply BPSK signal to both your carrier recovery subcircuit and your synchronous detector subcircuit. So BPSK signal first applied towards the square law device, which will do nothing but will going to square the incoming signal. So after squaring, we'll get the signal cos square 2 pi FCT plus theta. Here we are assuming that while traversing from transmitter side towards the receiver, we'll be having a phase shift of theta, and we are also assuming that the amplitude of the signal is unity. Then we'll pass it through a band pass filter, which actually produces this particular signal, 1 plus cos twice of 2 pi FCT plus theta by 2.
Band pass filter, which is tuned to twice of FC, also eliminates the DC power of the carrier waveform, and we will get the twice of the frequency of my carrier waveform signal.
Then we'll pass it on our signal to the frequency divider by 2 circuitry, which will give us cos 2 pi FCT, this particular signal, theta. If we clearly observe this particular signal, this is nothing but our carrier waveform with the phase shifted version by theta. So this particular signal goes through the synchronous demodulator and act as a carrier waveform. Then in the second portion of this sub block of synchronous demodulator, we apply BPSK signal, and another signal to this is the reference signal, which is nothing but our generated carrier waveform. One part of the synchronous demodulator output will go through the integrator, and another part is go through a bit synchronizer. Bit synchronizer, whose responsibility is to synchronize the bit up to the duration of TB. So this particular signal bt under root 2p cos square 2 pi fct plus theta, pass it on through the integrator. Integrator integrates this particular signal up to the duration of TB, which it collect from the bit synchronizer. Then after a particular duration TB, the switch S2 closed and this particular signal will goes to the decision making device. Whereas the decision making device, depending upon the value of this integrator output, decides whether transmitted bit was 0 or 1. As soon as this particular switch S2 closes and the output delivers to the decision making device, this switch S1 also becomes closed and it actually clears the integrator output towards the 0, and again integrator integrates the complete signal up to the next bit level. Coherent PSK detector can understood in two parts. Number one is your carrier recovery, as you have already studied. Then synchronous detection. The upper block is responsible for the carrier recovery. The transmitted signal undergoes the phase change depending upon the time delay from transmitter end to the receiver end. This phase change BPSK signal ST is equal to BT dot under root 2p cos of 2 pi fct plus theta is a common input to the square law device and the synchronous demodulator, where BT is the bit value, that is either 0 or 1, and P is the power of the carrier. The received signal is then allowed to pass through a square law device. Then this signal is then passed through a band pass filter whose pass band is centered around twice of Fc. Band pass filter removes the DC value of the signal and we get the carrier wave, which is twice in magnitude as we required. This is due to the square device. This signal is then passed through a frequency divider circuit which generates the carrier signal. Lower block performs the synchronous detection, which takes the input as the recovered carrier signal and the phase change BPSK signal. This signal again applied to the bit synchronizer and the integrator. The integrator integrates the signal over 1 bit period and the bit synchronizer synchronizes the bit duration, which is up to TB. At the end of bit duration TB, the bit synchronizer closes switch S2, which connects to the output at an integrator to the decision device. After a bit duration, the synchronizer opens the switch S2 and switch S1 is closed, which resets the integrator voltage to 0 and integrator integrates the next bit. We are assuming that 1 bit period TB contains integral number of cycles of the carrier, which ensures that the phase change occurs in carrier only at 0 crossing, and the BPSK waveform has full cycles of sinusoidal carrier. Although this is not always be the cases, but we are assuming that. Signal is then applied to the decision device, which decides whether the transmitted symbol was 0 or 1, and depending upon that we'll get the output. Then disadvantages of the PSK signal. To regenerate the carrier in the receiver, we perform the squaring of the received signal. The recovered signal is unchanged whether the input signal is positive or negative, even if the input signal has changed its sign. Since we are using square law device, so whatever signal we are applying to it, we'll just getting the squared. It means whether the input is +2 or -2, in both the cases output will always be 4, and it is not possible to characterize that whether input signal is +2 or -2. Similar thing has been applicable to it. It is not possible to find whether the transmitted bit was +BT or -BT. Hence, phase ambiguity is a problem in the demodulation of a BPSK signal. This problem can be removed with the use of differential phase shift key. Thank you very much for your patience here.